Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today because we are diving into something that pretty much every single programmer, software engineer, or tech enthusiast has wrestled with at least once. We're talking about code optimization. Today, we're looking at a genuinely fascinating Haskell optimization mystery, originally brought to us by a developer named Ang. We're going to uncover exactly what happens when a seemingly perfect textbook code refactor just doesn't go according to plan. So let's get right into it.
Right off the bat, we have to ask the million-dollar question. Does refactoring your code actually always make it faster? I mean, we all have this built-in assumption, right? We figure if we modernize our architecture, use a more advanced function, or cut out some intermediate step, the computer is just going to reward us with blazing fast execution times. We instinctively expect efficiency to follow this perfectly linear path. Better logic should equal faster software, period. But, as we're about to see in our source material today, the reality of how compilers and systems actually process our brilliant little improvements can be incredibly counterintuitive.
Section 1. The Refactoring Dilemma. Let's take a look at the specific problem we're trying to solve.
Okay, so the task at hand seems super straightforward. Imagine you've got this massive digital novel, and you need a program to count the number of volumes and chapters from a wildly long list of text blocks. The original approach uses a classic Haskell list comprehension. It filters the blocks, finds the volume headers, and then just checks the length of that resulting list. Easy, right? Well, the suggested refactor swaps out that list comprehension for foldl, a strict left fold, which uses an accumulator to keep a running tally of those volumes instead. Just glancing at the syntax, you can immediately tell the refactored code is longer, way denser, and definitely looks a lot more technical.
You know, when Ang first considered this change, the thought process was totally logical. Ang actually notes in the source text, and I quote, "Initially, while drafting this post and researching through the refactoring and optimization, one would thought the changes would improve the performance. And honestly, that makes perfect sense. You're taking a multi-step operation and replacing it with a highly specialized folding function that's literally built for iteration. On paper, this has all the classic markers of a massive refactoring win." Moving on to part 2, the list comprehension way. Let's break down how that original code is actually functioning under the hood.
So, the original list comprehension code operates in two very distinct mechanical steps. Step 1 is allocation. The program walks through the entire list of text blocks, filters out anything that isn't a volume header, and constructs a brand new intermediate list right there in memory. Since we really only care about the final count, it just fills this new list with lightweight placeholder units, those empty parentheses. Then we hit step 2. The program now has to walk through that entirely new intermediate list all over again just to count them up. Walk, filter, build, then walk again and count. When you think about it, that is a ton of manual labor for the machine.
And this two-step process brings some pretty glaring theoretical flaws with it. By building that intermediate list of placeholders, the program is just eating up temporary memory. Plus, when that list is inevitably thrown away after the counting is finished, it puts all this extra strain on the garbage collector to come in and clean up the mess. Now, for a tiny script, sure, it wouldn't really matter. But as Ang points out, when you scale this up to massive digital novels with thousands and thousands of chapters, creating that temporary list wastes a massive amount of memory and processing power.
Which brings us to section 3, the foldl alternative. This is where the big optimization is supposed to happen. To get rid of that wasteful temporary list, the refactor brings in foldl. And man, the mechanics here are theoretically superior in just about every single way. It evaluates as a strict left fold, meaning it forces evaluation at each step rather than putting it off until later. But the best part? It walks through the entire blocks list in a single pass. Zero allocation for temporary lists. None. Instead, it just carries this little integer counter along with it, simply incrementing it on the fly every time it hits a volume header. It's a beautifully elegant one-and-done operation.
Now, to fully grasp why forcing that evaluation is such a huge deal here, we need to talk about a specific Haskell concept Ang highlights, the thunk. Basically, a thunk is just a data structure that represents an unevaluated expression. Because Haskell is a lazy language by default, it sometimes prefers to build up these massive chains of unevaluated thunks in memory instead of just, doing the math right then and there. And when you're processing huge lists, this can cause major memory leaks. So the strictness of foldl actually forces the program to evaluate immediately, actively preventing that dangerous memory-hogging thunk buildup. And they actually took the engineering a step further. The refactored code includes this really specific micro-optimization. You might notice it initializes the accumulator with an explicit type annotation, 0int. Ang notes this is highly intentional, specifically to avoid Haskell's default integer type. In Haskell, integer can dynamically grow to an arbitrary size,
which makes it way less memory efficient and inherently slower to process. By explicitly demanding an int, the code forces the compiler to use a much faster fixed-size machine integer. Pretty clever, right?
Section 4. Apples in a basket. Let's visualize this with a really helpful analogy.
Ang gives us this fantastic analogy that just perfectly nails the core difference between these two approaches. Imagine you want to count the red apples in a huge mixed basket of fruit. The original list comprehension way, it's like picking up every single red apple, carefully placing them all into a totally separate second basket, and then, only after you're completely done sorting, you finally count the apples in that second basket. I mean, it's an absurd amount of unnecessary movement. The foldl way, though, is like just holding a mechanical tally counter in your hand. Every time you see a red apple, click. You just click the counter. No second basket needed. When you frame it like that, the tally counter approach feels like an absolute no-brainer.
But as we all know, optimization is rarely free. This refactor introduces a pretty significant trade-off by severely sacrificing code readability. To get that pristine single-pass performance, the new code demands manual handling of accumulators, it leans heavily on inline functions, lambdas, and it uses much more complex pattern matching. You're effectively trading simple, declarative readability for dense, technical complexity. It just takes a lot more mental energy for a human engineer to quickly parse what this code is actually trying to do. Interestingly enough, though, during this research, Ang discovered a bit of a sweet spot. An alternative rewrite using the simple sum function. So instead of building a list of empty parentheses placeholders, you build a list of the number 1 and then just sum them up. As Ang points out, this retains that high, simple readability of the original code, but it perfectly communicates the actual intention of the script to whoever is reading it, which is just to count the items. In a real-world collaborative codebase, that kind of instant readability is very often just as valuable as raw computational speed.
All right, Section 5. The surprising plot twist. Let's look at the actual benchmark results.
Okay, let's recap. We have the original two baskets approach, we have the theoretically optimized tally counter, and we have the highly readable sum alternative. We logically eliminated temporary memory allocation, we completely bypassed the garbage collector, we even used strict, explicit type annotations to squeeze out every single drop of micro-performance. So, when Ang finally took these pieces of code and ran a strict benchmark evaluation, did the optimized foldl code actually run faster?
Well, here is the absolute bombshell revelation from the text. It performed much worse. Seriously, just let that sink in for a second. The heavily engineered, theoretically perfect, single-pass, memory-safe optimization didn't just fail to improve performance. Without explicit optimization flags turned on in the compiler, it actually ran significantly slower than the original memory-hogging list comprehension. Literally, everything that made total logical sense on paper just completely fell apart in actual execution.
I know what you're thinking. How is that even physically possible? Well, Ang leaves us on a massive cliffhanger here. At the very end of the post, Ang writes, "However, we'll discuss this in the next post, as the post is getting longer and I want to keep the post at manageable smaller size. Till the next post, yours truly, Ang." So the exact deep-in-the-weeds technical reasons underlying why the compiler completely choked on this particular optimization is a mystery for another day.
But it does leave us with a truly fascinating final thought to walk away with today. If a tally counter is so clearly logically better than using two baskets, why does theoretical optimization sometimes fail so spectacularly in practice? It's just a brilliant reminder that we aren't just writing logic in a vacuum, right? We are interacting with immensely complex compilers, interpreters, and runtime environments that practically have minds of their own. Sometimes trying to cleverly outsmart the system just ends up getting in its way. Thank you so much for joining me for this explainer. Keep asking questions, keep experimenting, and I really hope this sparked your curiosity as much as it did mine. Catch you next time.